Okay, what I want to just take a real quick look at and then get you down, get you working on this stuff and getting some questions answered. I want to take another look at the chain rule. And remember what we did, let's kind of just put things in perspective here a little bit. Day before yesterday, we looked at the chain rule and really the important part of the chain rule, sort of the practical, how do I do derivatives, look at the chain rule. And that, we just call it the onion approach. Right? We're going to peel the onion from the outside in and just work. We're going to approach the derivative in layers, and we're just going to differentiate each layer. And each layer of the derivative adds another link to the chain that we're multiplying together, the factors. What I want to look at today is a little bit more conceptual approach to this. I'd be quick about this. But the chain rule can also be written like this. We could also say that look like this. What's that? Oh, is this it? Yeah, I'll take it. Thanks. Okay, so we can write it this way. Now, what does this mean? We can write it as a product of rates of change. Let's take a clock as kind of an analogy to how we can apply this. If we're looking at a clock, we could define some rates of change of the angular positions of the hands on a clock. Okay, so let's just say that we're going to let S equal the angular position of the second hand. M is going to be the minute hand. Same thing, angular position. And H, of course, the hour hand. As these obviously turn at different rates, right? Second hand is a lot faster than the minute hand, which is faster than the hour hand, right? We could define some rates of change here, though. We could say something like this. We could say ds dm. And what that means, it's a derivative, but a derivative really represents, in this case, a rate of change of these two different quantities. The way we would say that is the rate of change of the position of the second hand with respect to the position of the minute hand. Okay, now, anybody tell me what number that's going to be? It's going to be 60 over 1, yeah, right? Because when we're talking about angular position, we're just talking about rotations, or maybe even pieces of rotations, which we might call degrees or radians. But let's just limit ourselves to complete rotations. It's easier to think of that way, easier to see. Yeah, the second hand has to make 60 complete rotations for one complete rotation of the minute hand, right? Does that make sense? And that really tells us something important. That 60 is an important number. It's 60 times faster at rotating the second hand is than the minute hand. Okay. Now, what about dmdh? Is it 60? Yeah, think about it. Picture a clock. Yeah. Think about the hands on it. Right? It does. Now let's go back to this first one. If you can kind of picture a clock speeding up, an analog clock, yeah, the second hand would have to go around 60 times for that minute hand to tick through all 60 minutes, right? But what's this one going to be? How many times does the minute hand have to circle the clock for the hour hand to circle the clock once?
24.
Well, how many? 12. Yeah, I mean 24. I mean, if we had some fancy military clock, but it's so if it's a 12-hour clock, it's going to be 12, isn't it? Right? Because if one complete rotation of the minute hand means 1 hour, right? 12 hours on the clock. Okay, so now all we're saying with this chain rule, and this is an easy way I think to kind of put this together, if I wanted to calculate ds dh, what's the answer going to be? Yeah, 720, isn't it? Right? It's 720. Now, how did we get that? Well, we get that by the chain rule, because we know that ds dm times dm dh is equal to ds dh, and we know both of these quantities now, right? Now, there's a cool little trick here you can do. It's not really a trick, but it's just a different way of approaching this. And one of the really interesting things about math, and you start to see this at calculus, really calculus is where everything kind of comes together, and there's be a lot of those, oh, I get it, those aha moments happen a lot in calculus. One of them is that all these different sort of disparate approaches and ways of looking at things just sort of come together, and they all work together. Now look, if we look at this algebraically, if we consider these rates of change to be variables, and they really are. S is changing, the position of the second hand, M is changing, H is changing. So ds and dh and dm just represent little pieces of those changes, and they're variables too. Now, algebraically, what can we say about this if I'm just multiplying these variables, a ratio of these variables? What's happening algebraically here? Is anything canceling? The DMs are canceling algebraically, right? Well, that's convenient that it works out that way, that algebraic cancellation allows us to just rewrite this as ds over dh, but it's completely consistent. The chain rule works that way. You can cancel numerators and denominators within the chain rule, and you can sort of collapse these rates that way. It's really, it's a nice way to do it. And so we end up, it's very predictable, it's easy to use. This we said was 60, this we said was 12, and so we got our answer, 720. Now where this shows up on the assignment would be problems kind of like, let's see, I've got one up here. Okay, where we had something like this. How about, let's put this up here. Okay, so this is the kind of problem we're doing. Stuff like this. Find an equation for the line tangent to the curve at the point defined by the given value of t. So they give us x as a function of t, and they give us y as a function of t. And then they're telling us a value of t, and they want us to know what's the equation of the line tangent to the curve. Now, what's a way of looking at this here that's a little bit odd? Why would we define x in terms of t's and y in terms of t's? This is something that I wish we covered in sort of pre-calculus that we just don't get to. But this is called a parametric equation. Parametric equation just means that we're going to write variables, all of the variables in terms of a common parameter, usually t, or time. Now here's how we can look at this. Imagine that there's an ant crawling along this curve, and what we've done is when we're looking at x equals 4t, we're looking only at the x coordinate of that ant's motion. So imagine that we're staring down. We're staring down on this ant from up here. There's our eyeball. Looking down on the ant that's walking along some curve. But if we're looking from directly above, we're not sensitive to the vertical motion of the ant. All we notice is the ant's horizontal motion, right? Another way of thinking about that is if we were shining a light down from above, we're looking at the shadow of the ant on the x-axis. Okay? Either way, I think they both work. And then, of course, the other part of this, y equals a function of t, means we're taking a different perspective. That means we're looking from, say, over here. Right? Where y watching the ant, and now all we see is the vertical motion. Or we see the shadow of the ant if we shine a light horizontally on the vertical axis. And so our goal here is to try to combine those two pieces of information. The X picture, where we're looking from above, and the Y picture, where we're looking from the side, into one two-dimensional graph, right? Does that make sense? Okay, and so if we were to differentiate this, if X equals 4t, we could find the rate of change of X as a function of time, which is just the horizontal speed of the ant. What is dx dt? 4, yeah. So the ant if we're looking down on the ant from above, we see the ant is moving at constant horizontal speed, right? Okay, what about the vertical part? I think we had that. Y equals the square root of t. Yeah. If I want to find dy dt, what do I have to do first to this? Okay, good. I need to write it as power. T to the 1/2. And then so dy dt would equal what?
1/2 t.
Okay, so 1/2 t to the negative 1/2. T to the negative 1/2 is just going to end up being a t to the 1/2 on the bottom. So square root of t on the bottom. So I just have 1 over 2 times the square root of t. Now look what I've got here. I've got dx dt and dy dt. And if I'm trying to find the equation of the tangent line, all I need is a slope and a point, right? Well, the slope is dy dx if I'm graphing this in the xy plane. And so dy dx, I can use the chain rule for it, right? I can write that as dy dt times dt dx. Or, if I want to, I could write it as a quotient too. Instead of multiplying by dt dx, I could conversely divide by what? Dx dt, right? Because isn't dividing by a fraction the same as multiplying by its reciprocal and vice versa? So I could write that as dy dt divided by dx dt. Right? Either way I want to slice it, if I look at my derivative that way, if I calculate or evaluate the derivative here, I can either write it as dy dt we said was 4. Now, oh no we didn't. Sorry, I had it backwards. That was the fraction, right? So that should have been, there we go. Okay. Like that, right? Yeah. Okay. Dx dt was 4. Yeah, good. So if dx dt is 4, then isn't dt dx just the reciprocal of 4, right? So this just becomes 1/4. Or if I want to, I can just divide them, right? I could divide this thing by 4, which is the same as multiplying by 1/4. Either way, take a pick. But I get this product. If I multiply straight across, it looks like I just get 1/8 times the square root of t, right? Okay, that's pretty cool. That tells us now, as a function of time, it tells us what the slope of this curve is going to be, right? This ant is walking along this function, and now we could plug in a value of t, and we would know what the slope would be at that time. And that's really what the question is asking us to do. Then they go back and they say, okay, if t is 1/9, what's the equation of the tangent line? Well, plug 1/9 in there, right? How would we find a point on the xy plane? We'd need an x and a y value, right? Simultaneously. Sure, yeah, just plug in 1/9 in for x of t and y of t, and that's going to tell us at those snapshots in time, it's telling us what's the x value and what's the y value, right? So I'm going to leave it at that. But I want you to think, especially those of you who are kind of thinking, or in physics, think about this in terms of kinematics, maybe. Or if you're resolving forces down into the equations of motion, this is a pretty slick way to do it. When you've got these, this looks an awful lot like physics here. You're looking at you got to talk about projectile motion at all? Haven't gotten there? Well, you're going to. When you start talking about things like projectile motion, you're going to take the like velocity and position and acceleration. You're going to break those up into components. You're going to break it up into a vertical component. And for projectile motion, that's the component that's affected by gravity, and the horizontal component is unaffected by gravity. And so I'm giving you just a snapshot in the future here. As you're looking at this stuff, kind of just think about this too, because this is how you really do that stuff at a little higher level. Okay, but that's where I'm going to leave it. That's all we need for this class is just sort of how do you manipulate these parametric equations using derivatives. Okay, make sense? Maybe it will. Okay, let's go.